Hi guys, welcome to 214, which is data modeling with logarithmic functions. You've seen a little bit of this before. We actually did it back in 2.9 when we looked at Richter scale model and pH and Newton's law of cooling. We're just going to kind of expand on that a little bit and also look at logarithmic regressions. So these formulas, again, you don't need to memorize them, but they are different formulas that involve logs or exponentials that you may need to utilize. All right, so let's look at example 2. It says the amount of energy E in ergs that an earthquake releases is released to its Richter scale magnitude m by the equation log E equals 11.8 plus 1.5 m. And then there was an earthquake measuring 7.8 on the Richter scale struck southern and central Turkey. How much energy did the earthquake release? So the magnitude is m, and it tells us that the magnitude is 7.8. So I'm going to plug that in. And I'm just going to type that in my calculator, the right side, so I can get a number. So again, our goal here is to solve for E, which is the amount of energy in ergs. So I have 11.8 plus 1.5 times 7.8. And you should get 23.5. Notice that's not my final answer. That gives me log E equals 23.5. So if I want to solve for E, remember that's a base of 10. So it's going to be 10 to the 23.5 is equal to E, which if I type that in my calculator, it's going to be very big. We get essentially 3.162 times 10 to the 23rd power. Okay, you could also just leave it as 10 to the 23.5. That would be acceptable too. All right, let's look at another example. Oops. All right, this one deals with the pH. Okay, so on the previous page, it gave you the formula pH equals negative log of the hydrogen ions. Okay. So it says balsamic vinegar has a pH of 2.4 and baking soda pH of 8.4. So let's start with the balsamic vinegar. We know the pH of this is 2.4 equals negative log of the hydrogen ions. So I'm going to first divide both sides by -1. So I get negative 2.4 equals log of the hydrogen ions. Then I can just put this into exponential form and I get 10 to the negative 2.4 power is equal to the hydrogen ion concentration. If I did type that into my calculator, I would get 0.004 if we rounded to 3 decimal places. So that's for the balsamic vinegar. Then let's do the same thing for the baking soda. Maybe let's not use that abbreviation. Okay, so this one has a pH of 8.4, so that equals negative log of the hydrogen ion concentrations. Then I'm going to divide both sides by a negative. And then put it into exponential form. So 10 to the negative 8.4 is the hydrogen ion concentration of the baking soda. Again, you could also type that into your calculator if you wanted to. So part B says how many times greater is the hydrogen ion concentration of the vinegar than of the baking soda? So we said the vinegar was 10 to the negative 2.4 and the baking soda was 10 to the negative 8.4. Well, negative exponents can switch to become positive, which gives me 10 to the 6th power. Notice that when I am dividing with exponents, I subtract them. So 10 to the 6th times greater. So for orders of magnitude, it's essentially just what your exponent is. So that would be 6 orders of magnitude. Okay, cool. All right, let's do one now with Newton's law of cooling. So this is example number 7. This formula was also given to you on the front page, so I'm just going to copy it. This one's going to be pretty extensive. I will warn you of that, so make sure you are paying close attention and are fully engaged. All right, so this says a batch of brownies are taken out of a 375-degree oven and cools to 150 degrees after 20 minutes in a room of 70 degrees. Use Newton's law of cooling to determine how long it will take the brownies to cool, okay? So T sub 0 is the initial temperature, okay? T sub m is the temperature of the surrounding medium, is how they define it, or essentially what the room is, okay? And then T is essentially kind of what you're trying to find, and the little t is time, okay? So in this case, we have T sub 0 is 375. That's my initial temperature. Temperature of the surrounding medium here is 70 degrees because the room is 70 degrees. I know that after 20 minutes that the brownies cool to 150. So that means T of 20 will equal 150. And then we want to find how long it'll take the brownies to cool to 90 degrees. So we're going to have to do a lot of algebra to get there, but it's not going to be too bad. We're just going to plug in what we know. So I know that after 20 minutes, it'll equal 150. So I'm going to plug that in. T sub m is 70. Then I have T sub 0, 375 minus 70 just gives me 305. E to the negative k, and I know that that's after 20 minutes that cools to 150. So essentially my goal here is to find k so that then I have an equation that I can plug in for any time and figure out what the temperature would be, or vice versa. So to solve this equation, it's just exponential equation. I'm going to minus 70 on both sides. I get 80 equals 305 e to the negative 20k. Then I'm going to divide by 305. So this is a little bit of review of 213. So I get e to the negative 20k equals 80 over 305. I'm stuck right now. I'm in exponential form, so I'm going to put it into log form with a base of e, that's ln, of 80 over 305 equals negative 20k. And last step here would be to divide by negative 20. So this is a big, ugly number, but k essentially is ln of 80 over 305 divided by negative 20. All that was just solving an equation back from 213. So I'm going to show you how to store this in your calculator so that you can use it. So if you do ln of 80 over 305 and then divide by negative 20 and hit enter, you should get approximately 0.067, okay? Now, you can just scroll up in your calculator, but if you also hit, oops, not twice, this STO next to the 1, and then if you can store it as any letter, let's say I want to store it as A, that means anytime I go to type A, it will know that that's what I'm trying to use. So again, if your calculator doesn't scroll, or if you want to do a bunch of stuff in between, that can be helpful. All right, so let's go back to now what I know. Now I have a value for k that I can plug back in. That wasn't my end goal, but I needed it to get there. So what I want to do here is determine how long it'll take the brownies to cool to 90 degrees. So I want the end temperature here to be 90 degrees. And then I'm going to plug in everything that I know again. Okay, now I just wrote this as k, but remember I really know what k is. I don't want to round it, but you could just rewrite that as negative, what was it, 0.067? Yes. Okay, but I won't round it in my calculator. Minus 70 to both sides. Divide by 305. Okay, then I'm going to put it in log form. Log with a base of e is ln. And then finally divide by that negative 0.067. which is my value of k. Again, I'm going to use the exact value, not the rounded value in my calculator. So I have ln of 20 over 305 divided by alpha a. Again, or you could just scroll up. Okay. And I believe right here, this should have ended up being positive. So somewhere I missed a negative in there, but that is correct. It should be 40.717 minutes. Okay, so that's how long it'll take the brownies to cool to that temperature. That is something that you do need to be able to utilize and do. So make sure that you are familiar with that context. All right, let's look at one more. Let's look at a log regression. Okay, you're hopefully pretty familiar with regressions at this point. So what I'm going to do first is I'm going to type all my data into my calculator. Hopefully we know how to do that by now. Stat edit. Okay, 2, 3, 4, 5, 6, and 7. Okay. Now, if you notice, there's not one that says logarithmic regression, okay? So what you need to use is number 9, which says ln reg, because think about ln is a log. It's just a log with a base of e, okay? Part B, logistic, that's completely different, so don't do that. Number 9. All right, so I have L1, L2. I'm going to go ahead and store it. Vars, y vars, function y1, and calculate. And it'll give you it in the form a plus b ln of x. So let's go ahead and copy that down. I don't have any context here, or else I would define my variables as x and y. Okay. All right, part B says use the function to predict f of x when x equals 10. So all I'm going to do on this is I'm going to go vars, y vars, function y1. And when x is 10, so I'm going to plug in 10 essentially to my y1 where it's stored. And I should get 8.07. This does say round to the nearest tenth for whatever reason, so that would be 8.1. All right, this one, what is the residual? Some of you guys missed this on your last test. Remember, the residual is the actual or the observed minus the predicted. The actual is what data you are given or what data is in the table. So for example, this point right here, my actual y value is 4.5. That is what is actually true. The predicted is what you're going to find by doing y1 of 4. So again, to get the predicted, I'm going to do y1 and put in parentheses 4 because that's plugging in 4 into my y1 function. And I should get about 3.806. That is the predicted value. What you find by using your model is your predicted value. So actual minus predicted. So I do 4.5 minus this whole thing, and you get 0.694. That is the residual. One sort of follow-up question on this is this a over prediction or an under prediction? The easiest way to think about this is to say, well, my prediction was lower than my actual value, so therefore I under predicted. Okay, the actual was 4.5. I only predicted 3.8, so I under predicted. Okay. So again, this is just an overview of modeling with log functions. Sometimes it's just doing an equation. Sometimes it's doing a regression. Not equations you need to memorize by any means, but you do need to be able to utilize them. So that wraps up 214. Have a great rest of your day.